time we talk about the model selection criteria or scores that could be used to evaluate whether or not our model can achieve the good fitness, and that shall be measured by the loss term, and as well as whether or not the complexity of our model is enough, or whether or not it is increasing to the point that it could cause the problem. And that shall be measured by the model complexity term. So this is something that you should keep in mind, because it will be like a topology, or maybe it's like a format of all the model selection scores that you will learn today. In fact, all those terms that highlight in green here are related to the fitness. Okay, I'm not sure if you can see that. It's like the fitness of the fitness measurement, like the loss function, MSE, and in this case, because L here is denoted as the log livelihood, that's the reason why we have to do the negate. And usually because we assume that the log livelihood came from the Gaussian probability, that's why we negate 1 and also multiply with 2. Okay, that's it. Okay. And so today we will go over some of these scores function just to describe something. And I would put it this way. The following analysis could help you make a decision whether or not a model A is better than model B, but many of these scores aren't used that often. And that is because these days, especially when our model is big and we do the very, very large amount of training, it's better to use like a mean square error, which is like, and do the validation like the one on the bottom right here. Yep. Anyway, I will do a little adjustment. Just give me a moment. That's it. Because in my iPad is in the correct side, but up there is like toward the left for some reason, toward the right for some reason. Yeah, and I'm not sure why. Okay. อีกรอบหนึ่งไม่รู้ว่าเป็นอะไรนะคะแต่ดูจากเว็บเพลย์ I cannot really tell what's the reason that it looks like this. Anyway. Right. Okay. Okay, so for each score, we will start from AIC, BIC, and AICC. Well, AICC, the little c here came from the corrected AIC, and AIC is from the name like Akaige information, right? And AICC is the corrected Akaige information, and for BIC, it's Bayesian information. These scores are actually quite similar in the sense that they have like a loss term plus model complexity. They are very, very similar, except the last terms. This last term actually related to the model complexity, and actually the corrected Akaige information. This one is often added when the amount of training samples are small, or number of m's is like a number of measurements that you use to train a model is small. So we normally add this term. Otherwise, if you think about if m is large, right, then that means that this term will approach 0, and the correct Akaige will become just the Akaige information criteria. If I remember correctly, Akaige is the name of a Japanese scientist who invented this function. Yes. Okay. And that's how these two terms are related. And the reason that we have to know a little bit is because, if we end up having two models that achieve the same fitness, I'll put it this way. If we have a model that achieves the same fitness, we probably want to select the one with the lower complexity. Or maybe if we achieve the same complexity, we want the one with a better fitness. And actually there are like a multiplications of the differences between model A and model B. For example, if we have like a same loss function, sometimes we want to know like sometimes we have this loss term and we have this complexity term, and sometimes we want to see how better the second model that is more complex need to achieve the lower loss in order to make it selected. Sometimes you need this kind of decision making. But anyway, okay, let's go over each of them. Okay, let me see. Okay, let's start off with the fact that we have to compute the loss function first. Okay, and that loss function came from this KL divergence, and as I mentioned before, it's like a likelihood between the model versus the true density. Okay, and let's say you want to estimate alpha, which is a model parameter. And when you calculate the KL divergence, here's the formula for KL divergence, and actually you could look up the definition for the Kullback-Leibler divergence. Kullback-Leibler divergence is like a measurement of the difference between two probabilities. And usually they use when the two probabilities are sharing the same formulation. For example, if you assume that the true model is a Gaussian, the true model is the one above. If you assume that the true model is Gaussian, you normally have this, like a model, probability model for your machine learning to be Gaussian as well. And with that, you can cancel out some of the parameters, or maybe you can reshape the formulation such that this integration becomes a closed term formulation. So let's see. First, you don't need to take any lecture right now. Just see how it progressed from this KL divergence to the loss function that you will use in your model selection score. Okay, maybe start from that first. And once you have this model selection score, maybe it gives you a better idea of what this L is. Because I believe that, when we look at this formula, we can assume that L is definitely like an exponential term of the Gaussian. but okay, maybe let's see where it came from. You don't need to take any lecture. Okay, first we have KL Kullback-Leibler divergence, and in this case we use the model, the probabilistic model of our ground truth as the one that is like as a denominator, yeah, and it will be the one that is used as like target probability in averaging in this case. So after that, because you use the ground truth probability as the reference in averaging, when you reshape from this KL divergence form into like expectation, the term that you will be using in calculating the average will be the log term, right? After that, okay, when you have to minimize the KL divergence with the alpha that you estimate, you will then try to minimize this expectation. That's the second thing. And because your ground truth, you know, the probability of y given alpha is actually unrelated to your variable that you use in optimization. That is this one. And that's why sometimes people will reduce from this form to just the expectation of the probability of the model, and they have a negate right in front of it because it came from the fact that you're calculating the expectation of the log. Okay, I'll put this as A and this one as B, log A minus log of B, but it just turned out that, sorry, log of B, and it just turned out that this one is like constant. And therefore, when this one is constant, you don't look at it, then it becomes just that's it. That's why it becomes this term. Okay, and therefore your optimization will be targeting towards this negate expectation. Then we can further simplify this expectation, because if you think about that, if you have to compute this expectation, it's like you still have to go back to do the, you know, the integration of the probability of y given alpha star, right, and the log b dy, which can be very hard to calculate. That's why they further simplify from this negate of expectation using the law of large number, the strong law of large number. And for those that studied the estimation theory before, I remember mentioned something about this term, but if you cannot remember, that's fine. Anyway, because we have this strong law of large number applied, we then further formulate this one, simplify this one, this term, into the limitation of 1 over m sum of log of the probability of the model parameter, and which is turning out to be this one. And don't forget the negate, it will come with it. And because you are doing the argument of the negate term, you turn it back into the argmax. Then you have the argmax of the limitation as m approach infinity, right? And as m approaching infinity, that means that, you know, it's like, and sum of m here is like, it is as if you are trying to optimizing just this sum of log over here. That's it all. And that is like, if you have a high value of this term, it's just like your alpha is fitted to your measurements y. Yeah. That's where that log likelihood loss came from. Shall we go? Okay. So everything is written here, don't worry about it. After that, we will then further simplify this log term. It depends on what probability that we are defining over it. Let's say in this case, we will use like a generic Gaussian, right? And because of that, we can assume that the model that we want to estimate, this alpha, is somehow going to be related to the mean value of our y measurements. And with that, we turn this logarithm term into this sum square. And because this f of x here is using to estimate the model parameters, and we kind of assume that it will be the expectation, and because of that, we could just approximate this denominator as if it is like a multiple of the variance. This term will have some kind of steps, as in it's like a rough approximation from that to that, just a rough approximation. And because of that, we can see that, okay, the only thing that is going to be related to the error here is the multiply of the maybe m sigma square, and we can approximate it with m. And here m is the number of your measurements or number of your training data. And once you have these, you can plug it in to your original AIC. And actually you can do the same thing for AICC and BIC. You can see that if you have two models, and maybe that two models are having different complexity, actually your best bet is that your L will be somewhat the same and maybe have some variance. That is like the term that could be different between two models. So if you are comparing two models, okay, I'll put this way. If you compare two models, your two models will have like, how should I say? It's like it will have each of the laws and the model complexity. Sorry, D should be N here. Let's say if I plug in each of them. So the first loss term plus m of the first model will be this, right? Because that is just the log of the 2 pi and sigma. I just separate them. And for the second model, you will have the same formulation, that is m of sigma and m of log 2 pi. Right, plus m. Because if you are using the same number of training data for the two models, that is normally the case, right? You have the number of training data and you just have two different models, you probably have the same m. But the thing that could be different is the n, the number of parameters involved with each of the model. And as you compare each of them, okay, if whatever you want to estimate here is like, it's representing the mean of your measurements, then definitely what you may have is like your 2 sigma may be close, but not exactly the same. But m over 2 pi and m here will be the same. So you further eliminate the term that could be cancelled out. And at the end of the day, you will have the fact that, you know, the two AIC for two models could be written as a difference between, you know, the complexity and m times log of the sigma squared divided by sigma prime squared. Let's say if the sigma prime squared is the let's say the error or deviation associated with the second model, and the sigma is associated with the first model. So if you want to choose model number 1 over model number 2, you should make sure that, okay, especially if your first model is large, you should make sure that this one will somehow, if you want to choose the first one, that means you should somehow make sure that this error of sigma will be lower than the sigma pi. Because with that, log of something that is less than 1 will be a negative value. So that is the main message of this slide. So it's about how you would choose one model over the other, especially when you have two complexity, and definitely the fitness could be different. But if you have the same fitness, let's say you have two models with the same error, this term will become 0, right? And then you only have this. It depends like which model you want to choose. You probably want to choose the one that will reduce the loss, not increasing the loss. But if you have the same model, right, you definitely go back to just considering the log of the sigma. Okay. So that is like the meaning of these differences. So maybe in the exam, would ask you to do something like, if you come up with this difference in AIC, which one would you choose and why? That could be, or maybe can you tell if one n has to be larger than the other n with some multiply? That could be the question in the exam. Yeah, the same thing go for BIC score, but BIC score is definitely kind of easier, as in if you don't want to, because I already derived what is log of the alpha. All you have to do for BIC is like you just compare those terms. But I think at least we know the fact that, okay, this is how loss function came from. Maybe, I'm not sure, but I think in your homework, we don't have this question anymore. We used to have a question about, can you compute the loss of AIC and BIC? But oh yes, you don't have this question anymore because I already make that coding for you in the homework one. AIC, BIC, all of that is kind of like the main one that we use. But you can compare this AIC and BIC score in your model that you have trained. So you can do it like manually in your homework as well. Yeah. I think that is all. That is like the main point of the detail of the model selection scores today. For the rest of that, it's like what is, it's like giving you the detail about what is this model selection score, what is that model selection score, and what are each of these terms. It's not that important in my opinion. You can look at them, you can Google it. Maybe a little more important than that is like this adjusted R-square. So the adjusted R-square will have this additional term. And maybe as your homework, just go back and check if m is very large, does the adjusted R-square turn to be R-square? It's very simple like that. Because I don't know how to say this, it's like everything you see here is already in Wikipedia page. There are tools to compute it for you. You don't need to do it yourself. So it's not that important to know what it is, in my opinion, but you just need to know how to analyze it. That's all. Okay. So, or you can, alternatively, if you want to use like a package to calculate each of these scores for you, you can visit this site, and actually there's a package called Stats Models that can do the calculation for you, train the model for you, and everything. But in our homework, I kind of did all of that manually, so you can see where it came from. All right. And actually, our main point today is about linear regression. And I believe, I forgot to change the first page of the slides. Anyway, can I have like a 3 minutes break? Just a little bit because my voice is going back.